3, 2, 1.
Cool. Thank you so much. So yeah, my name's Eddie Atkinson. This is Mike, Karam, and Jocelyn, and we're team seeking a route, or a route, depending on your persuasion. And we're doing challenge 1, which is to do with emergency dispatching. So fundamentally, I thought I'd start with what is the problem we're actually solving. And the problem we're solving is someone sits in a dispatching room stressed out of their mind, routing hundreds of resources to hundreds of potential incidences with varying severities and requirements. And these people are stressed, they are human, they're tired, and they're probably making mistakes, unfortunately. And those mistakes at times can be life-threatening. So fundamentally, what are we doing to fix that? Well, our solution is not deleting humans from the equation, as so many AI proponents would suggest. It's actually giving them the tools to do their jobs more effectively, safely, and efficiently. So how are we doing this? Well, we are using no magic, just mathematics. So we're using mixed integer linear programming, basically to create an optimization problem for routing resources to incidents, optimizing for prioritization, so whether an incident requires an immediate response, urgent, or it's just routine. Capability matching, so you don't really need police dogs for a traffic stop, but you might need them for a manhunt. Right? And distance minimization, so using up-to-date Google Maps traffic data, we're basically optimizing for how far away a resource is from an incident and what can get there fastest, basically, in addition to the prioritization and the capability matching. So I'm going to kick it over to Mike to show us actually what we've built, and yeah.
Thanks, Eddie. So as he's mentioned, we didn't just come up with ideas, we also built the system. So as you can see, we have various resources distributed across Western Australia. And as time moves forwards, you're going to see these pins popping up, and what they represent are various incidents occurring through time. The colour of that pin corresponds to the severity or urgency of that incident. So a blue pin is a low priority and more red means a higher priority. What happens is as these pins appear, we take the positions of the incidents and we take the positions of the vehicles and we run that through our optimization algorithm to find the optimal matching between the vehicles and the incidents. And we do this dynamically through time as the incidents occur. So what can happen is you might be assigned to a low priority incident. You're driving, and then our system detects a critical incident has just occurred nearby. So what's going to happen is that's going to run through the optimization algorithm, and there's a pretty high likelihood that you'll be rerouted to the higher priority incident. Furthermore, to illustrate that this is truly dynamic, what we've done is we've implemented an interactivity system, so you can drag and drop the vehicles and see how that influences the rerouting and how our optimization system deals with different situations. If you have any questions, we're more than happy to answer. Thank you.
I've just got a quick question. So if I see this right, if I understand it, when you drag and drop a vehicle or a new incident, is the whole model then run again, the whole programming model to minimize the distance for everyone?
Yep, so the mixed integer programming model, which is being run in our server, that actually takes only a few milliseconds to run. So we're not computing hundreds of thousands of matchings.
Yeah.
We only have like a few hundred potential vehicles, so it doesn't take too long. So yep, we just rerun every time.
Yeah, wow.
Very quick.
So have you got any ideas in terms of how far you can scale these algorithms? Would you be able to scale it in terms of the sort of realistic scenarios?
I mean, a little bit of my background. I used to work in energy optimization, and basically the whole entire Australian energy grid runs on a large linear optimization model. Oh, no! Yes!
Yep, hey everyone. My name's Mitch, and I'm with my team here. We took challenge 1, trying to optimize the pathing of many responders. I really like computational modeling. This is building massive simulation models. We did bite off a bit more than we could chew. So this is the command and control interface that we tried to create, and we would have a bunch of shortest path modeling, particularly using the A-star algorithm. So we had a bunch of algorithms in our model here. And it was dynamic as well. They would calculate the shortest path at each road intersection, so that would avoid traffic because they would account for that. And then we used a graph-based solution to have our cars move between nodes representing road intersections and edges representing the roads, and trying to make it as practical as possible. Yeah, that's about it. Thanks.
Thank you, well done.
Any questions? Any questions?
Hi everyone, let me introduce you to WA Poll Responder app. So our solutions, there are three main components, which are first, the optimization algorithm, second, the WA Poll Responder app that can send the real-time incident notifications to the frontline officers, and the third one is the management dashboard for the control unit. Our optimization algorithm, we decided to use Google Map API because we believe it's the most reliable source right now, and it can reflect the real travel time by taking traffic conditions or road closure as a factor. So this is the allocation result from us. For example, this incident is happened here with the type of incident E that required capability 3 and 2. So our optimization algorithm will allocate the resources from this is a closest distance, and also another one from the police station number 2 with the travel time less than 6 minutes.
Next, we have built this app, which is basically for the frontline officers. This app basically has this notification system. So if an incident happens, then alert comes onto the app, and then the responder can navigate to the location of the incident. We also have this live map feed, which basically allows the responder to see what's going on in the city. They can see what accidents are there, what capabilities are available in the city, and what police stations are nearby. When the incident comes, we have this option of either accept or decline, which can be managed. And then you go to the report where you get the information about the incident. So the basic information, what's the coordinates, what's the type of incident, and where it's happened. Then you have a map. And then you also have a navigate button where you click on it, and it can take you to the location of the incident. Next, we have a dashboard.
So we also create a dashboard, a real-time updated dashboard for the current incidents or the status of what's going on at the moment. So we could filter it on the right side with the stations, and we could see if each station has this certain number of available capabilities, or if it's in maintenance or it's already deployed. We could also see an ongoing job of specific capabilities that are currently assigned to a specific incident. And we could also filter a specific incident ID that shows what the algorithm has allocated, which capabilities the algorithm has allocated to a specific incident. So for example, with incident E, it's allocated capability 2 and 3 to a specific incident. And we just felt that this was important for the back-end users because the algorithm doesn't always take into consideration special cases where higher frequency of incidents happen in a certain area. So then the control unit or the back-end users could manually implement or identify these locations that they could.
Introducing Blue Flare. Blue Flare allows you as a police officer to get a green light from your current location to the incident that is happening right now. It provides a safe and optimised route between responding police vehicle and a priority 1 and 2 incident. How do we do this? We utilise the Main Roads SCATS traffic system, which is the system that controls the network of traffic lights across the CBD. And we can use this system to control the timing and the colour of the lights along the route that the police officer must take to ensure that that police officer gets to the route, gets to the incident as quick as possible and as safe as possible. This is a demonstration of our prototype application, which you can see on the left, and the current solution, which is Google Maps. As you can see here, Google Maps takes 8 minutes to get there if you ignore traffic lights, and with our traffic optimizations applied, we can reduce that time to 6 minutes.
And that's not all. Because we can do it for one, we can actually do it for multiple, and we have done it. We built a dashboard to build with an ML algorithm in order to optimize the routing across the traffic network.
So Blue Flare aims to assist police with responding to priority 1 and 2 calls within 12 minutes for every call, and meets community expectations. Those expectations means responding to where and when the community needs the police most, and providing the public assurance of immediate safety and support.
With further development, this system supports a wide range of additional capability. Number one, we can integrate with the existing WA police systems, incident management systems, bringing all that information into one place and really having that centralised control over the incidents that are happening right now. Number two, we can enable information sharing across the 3 emergency management organisations within WA for a better collaborative approach to incident management within the area. And number 3, we can look at some advanced algorithms like what have been previously discussed during the previous presentations, as well as some additional approaches like locking intersections out so a police officer can go on the other side of the road safely and make it even quicker to the intersection in question. Thank you for listening.
Our predictive control teams. We are going to be presenting the challenge number 2. The objective for this challenge is going to be develop a system to predict current location of stolen vehicles using the data, synthetic data that the police are giving to us. Our outcome with this project is deliver a potential pathway that the vehicle could take, or in this case, the police will take all the models. The model that we use for this project is LSTM. It's a model that's designed to recognize patterns in sequence of data, and also this model stores remember important information for long periods for the model. So what we did in this project was we start extracting the data, the coordinate from the path. Then we extract we use these coordinates to future predictive model. We train the model and then we test it.
So the first thing we did is to map the whole data that we got from the data. So you can see that we mapped all the data itself, and one of the predictions that we got was down here. So one of the test data that we got is that when one car was given, when the data was run, the red line showed that that's the best way to predict it. But one of the things that we've got was the model was needed more. It had a bigger error rate, and the predictions were pretty low a little bit. But with time, we can try to increase the accuracy. We can also see on the map itself, we only got one pathway. We can try to get more possible pathways that the police can use to predict which path to take. And with more data, we can add like weather and traffic to help, because traffic and weather affect the traffic from one direction to another. So with those considerations, we can try and get more accuracy. And that's all. If you have any other questions, you can ask.
Hi. A stolen vehicle not only represents financial loss, it also represents a security public problem. That's why our tool offers a new hope in terms of helping the police to divert their efforts into the areas that is more likely to be successful, especially during the first 10 minutes after the event has passed. We have developed a tool that takes in account many different variables, such as the traffic conditions, the road, the speed limit, and the quantity of traffic lights. So using the power of the geography and combined with the flexibility of the analytical process, we have developed a tool that provides a spatial guidance. This spatial guidance will help not only the people behind a desk, but also the agents that are in the field managing the emergency, in this case, the stolen vehicle. So we can see this in action. So first, an event is triggered. This event could be triggered by a camera, by a police report, by a phone call, no matter the source. After that, our tool takes the last known location as the input for the model, which start to calculating all the probabilities for a given or for a bunch of given intersections along the map. So these intersections are calculated using a regression model, a geographical regression model for each intersection based on speed and traffic and other kind of variables. So in the end, this is in real time. Every 30 seconds, as you can see in the demo, every 30 seconds we are calculating what is happening for a given vehicle, and this takes also in account the bearing and also the speed. So it's really powerful and it's really helpful. But what happens is if a vehicle is outside, that might happen eventually. So we also are capable to draw an area, a hotspot area, which is based also in the given location and the speed based on the previous data analysis. And with that, the police, the agents in the field are capable to really understand in a really easy way where to go and how many resources needed to achieve that. So there are a lot of other kind of interesting features in the application, like the list license plate. We are able to extract that data, but this is not the end. We can scale this project using more information like video data, image data, other kind of source data, for instance, suspect data, other kind of database that we don't have access at this moment, but the model is capable to adapt to this kind of information. And finally, we would like to hear more about this. Thank you.
Well done, awesome work.
There is method in madness. Often when we examine people's behavior, we don't understand why they do the things they do. When you look at how someone who's stolen a vehicle or committed a crime behaves, it appears that they have no plan, that they're just lashing out. But for thousands of years, humans knew almost nothing. We thought magnets were magic, which they are. And now we're starting to see that there is so much more to learn. There is more things to understand behind all the noise. With Bapu, we would examine the migration patterns of large amounts of vehicles in a metropolitan area, and we would then look for outliers to these migrations. Taking that data, we would then assume that these people were adrenalized, and from there, we would take that into a different training set and try and gain insight into how do people act when they are feeling their heart racing. We know that this would work. Humans are machines. There is data out there. This can be scaled to incredible amounts of things. The applications are in emergencies, they are in crowds, they are anywhere there is people and pain and anxiety. This is something for the future. This is something that will and can save lives.
And onto the application, we created a dashboard basically showing the locations of ANPR readings around the city. The green lines are not actual predictions, they're just representations of what the predictions could look like. And in order to do this, I have a proposal of collecting the data using data engineering essentially, and then going on to generalized RNN architecture. The model is called Flashback. It was proposed quite recently in a research paper, and achieves much higher accuracy than most RNNs or GRNN architectures. So, yeah.
Thanks, Connor.
Hi, my name is Lauren. I'm here with my classmates From ECU. So we decided to work on a virtual assistant for the police officers who will be in the out in the field. So with our limited knowledge on coding and machine learning, we managed to make Flowwise run and activated a chatbot for our police using the regulations that were provided to us by our mentors. And then I'll let Nyasha.
Good day. So basically what we managed to do was to create two applications, but they both do the same thing. One is fully on code, running with Python, using a local large language model called Llama 3. And we created a RAG pipeline, which is just to enable us to be able to collect data from a data source. The one that we used was a PDF document. Then from there we can be able to segment the document and the data from the document and send it to a vector database and be able to query from there using the capabilities of the OpenAI API without sending any data to it. Then the other part that we're going to demo now, because we had limited time, we couldn't continue with the code side, but given more time, we look forward to continue with it. We did exactly the same thing, but using a low-code solution, Flowwise, where we were able to replicate the same RAG pipeline, where we created this virtual chatbot. So basically, what you can see is that we provided it with legislation specifically to do with electronic rideable devices. So we are able to ask our chatbot within that confined space, so it shouldn't answer anything outside of that. So you'll see from the examples here that we have, where at one point we asked for pizza from the chatbot, and unfortunately it couldn't give us pizza. Yeah. As it says, I'm specifically a chatbot that deals with legislation on electronic rideables. Then there's other things that we are able to see where it has like ability to reference the sources that we provided clearly and correctly without hallucination, and it is able to give specific details. For example, if you are to ask, if I see someone with an e-rideable, what dimensions, what can I look into it to see if it's roadworthy or if it's now considered as a motor vehicle, or is it still considered as a scooter. It's able to give all those details and what are the fines and infringements that one can be given in specific.
Thanks, team.
Hi, good afternoon, everyone. So I would like all of you to just imagine a world where our frontline officers have an intelligent partner by their side, guiding them through the complexities of drug trafficking pursuits and legal protocols in real time. So we Team Millennials would like to present you our cutting-edge virtual assistant for the police officers designed to revolutionize law enforcement efficiency and effectiveness.
So here we have tried several large language models. So we have thought of integrating mobile app to the large language model, which we can train questions and answers and to provide the correct answers. So basically here we have to deal with legislations. So basically the main criteria we have thought is to give the correct, accurate answers. So for that we have tried several large language models, but we have came up with GPT Neo, which is like a latest one, and you know ChatGPT 4. It is quite similar to that, and the main thing is this is open source, you can freely use that. So here, this is kind of like a bootstrap UI we have a thought of integrating with that. And when it comes to integrating this large language model GPT Neo, you need a lot of processing power, RAM for that. For that, we have used Google Colab for that. And also when we have running the demo, I'll show you how we have used that. Yeah, so in the first place, we have used but it's kind of another large language model. But we feel like the accuracy of this model is not far enough to attain to our solution. And then we have tried another model called GPT-2 also. So that also not reliable enough to provide the correct answers, and also you have to train more question and answer pairs. And also I can show you the model that we have tried, GPT-Neo, that is our solution. So that gives more accurate answers. So we have trained multiple layers of question and answer pairs to give correct answers. So yeah, so I'll show you the outcome we have trained here. Yeah, so this is the one. So we have given the questionnaire, and then it provides the correct answers. So we have thought of so this is here we have used the Google Colab, and we have integrated open URL to integrate that. Thank you.
Okay, welcome to Red Hat Search by Control-Z. We researched and designed a dual proactive and reactive approach for a platform where analysts, officers and detectives alike can extract key information about police operations and incidents. There was a focus on the proactive, so the usage after a crime, e.g. analysts looking back, but there are also reactive aspects, for example, officers being dispatched. So we consulted the stakeholders very thoroughly and considered the real-life application. So our entity relationship diagram was designed to factor in these other internal data sources, which were identified through this consultation with the stakeholders, as well as the internal platforms which we were told about. So we made use of a custom LLM that uses the Anthropic API to generate a response based on the selected context and the user's query, including image analysis. This is a pre-existing tool that we had available to us. As a result, we focused on the front end and the user experience. So some key features are a secure API and an NLP to extract summaries and key information. So here you can see a PNG file going in and showing some output, but there is also the potential and the use for a CSV to go in and create summaries. So moving on to our high fidelity prototype. On the front page, there is a dashboard which displays the latest updates. Just a note, these are not in real time at this stage of development. So this provides the opportunity for a quick glance so that you can determine what is most important to you in your role at WAPOL. There is also the ability to filter. So for your need, is it risk level, officer name, or the operation? The modal allows for a slightly more in-depth view, and further to that, the operational information allows even more detail with potential links to other suspects and other cases. The search functionality at the top of the page can provide the opportunity to search for, let's say, Tom, and we notice that Tom is also linked to the red hat, and we want to look further into that red hat. So, where to next for this tool? We would be looking at implementing the backend server to create the secure APIs and URLs, implementing the NLP to extract this key information and the summarizations so that it can link to the dashboard. We would also look at further implementation of filters and logic so that it can suit an effective use for all types of personnel within WAPOL. We would also love for our latest updates to be real time. So for example, as the crew who are out on the ground are sending messages, this could be updating and pre-populating. So the search results would also provide a graphical interface for a visual representation of the data, and we would look at using something like the D3.js library. So ultimately, Red Hat Search assists you to make the connections that you don't know existed.
Good afternoon, we are Team Jellyfish. Today we are dealing with the number 4 challenges, which is extract all the key information. So we actually successfully resolve all the challenges by realizing all the objectives. How we do that? First of all, we use our open source tool to create a customized large language model then we can recognize the entity, then we can extract the relationship or the summary timeline, then we do the visualization. So how do we do that? We are technically innovative. Why? Because first of all, we recognize our entity. This is the raw data from all the investigative chats. So we color them, and then we can make a list of all these entities so that people can know. Then we extract our relationship. So we color them different entities by different colors so people can easily be seen in this picture. So this is the summary that we extract from our algorithm. As we all know that suspect is the most important item in every investigative chat. So we prioritize the suspects in the first beginning. This one is the timeline that we extract, so it looks like in this form as well. This is the dashboard that we developed for our algorithm. First of all, we can enter the entity of interest. For example, I'm interested for a person whose name is Jason M. So then all this Jason M pops up with their information. But actually this inquiry research, this inquiry form is not exclusive, it's inclusive. So we can combine them. For example, I search Jason M and sedan, that they will pop up with the information only fit for these two inquiries. If I tap into the information, then you will have all these details of this case, which we extract from our algorithm. And also we have a hangover summary, which hinted by Steve, because he said that we need all the hangover summary that the officer knows how the progress of the investigation. So I think our prototype is practical. First of all, we solve the question, and we also want to integrate it to the OneForce, the IMS, and IRIS software, which our WA Police is currently using. Then we can transfer our data easily and then make our picture very easily. And also we want to make it easy of use because everyone have different capacity. And it is a rough prototype. We will develop that in the future so that we can have more developed function as well. At the end, what our solution, we must have an outcome. So what is our outcome? We want to align with WA police vision, and then we want to enhance the community safety by quickly locating and arresting the suspects.
Hello everyone, so this is our presentation for the problem 4. So our project is about the crime chart log visualization dashboard design, and our project name is Tip of the Iceberg. So come to the overview of our system design. So we have 7 pages. So the first one is the overall dashboard. We will show all the database information. And then we can come to the chart logs overview as the cards. And then if you are interested in one of the single chart log, you can just by a single click, you can go into the single log dashboard to show the information. And also the last one, we have the correlation analyze. It's a combination of chartboard and also the 3D knowledge graph, and we have some additional pages of also. So this is our program. So first thing, we have a dashboard here. It will show all the information in general. So this is all we can get. We can get the location map view, the chart log history, and also the categorized active chart logs. And then if we come to the details, we can see all the cards, and we can show more. So also we got the summary here for the key information like the category, the date, and the case summary. So if you click into it, we come to the analyze dashboard. So you can show the chart log summary of all the messages. And we also, to show a history line for all these messages, you can also reverse it. And also, come to this part, we will show the entity relationship. So in this part, we try to rebuild the truth by the timeline and the location. So you can say, just by a simple click, we can generalize the, we can generalize the GIF to simulate the root generation of the suspect and our crime. And also, come to the next part is about the smart database. So in this part, it's kind of different. So we make a combination of the chartboard and the 3D the knowledge graph, and we show the information of the nodes and our relationship. Also, we show some examples. You can just by a simple click, you can go into it. So the first example, you can explore a single chart log, and you also can explore the correlation between different chart logs. And also, we allow you to interaction between the different entities, so you can find among the relation between all the locations and the persons and the events. So we use the chatbot actually as a search bar and a filter bar. So in this part, the design idea is quite different because we want to limit the AI's ability to generate the result because we're not looking for the correct answers. We're looking for much more possibilities. So just like our project name today, the tip of the iceberg. So because sometimes the missing part is much important than the obvious part. That's all, thank you.
So, my car was broken into last Easter, and even though it only cost me $100 to fix, it scarred me a little. So there's still broken glass in my backseat. But that's made me join all the Facebook community groups and start tracking different break-ins. But there's not enough information to put it into an AI, and that left me a little disappointed. But coming into this hackathon, I was exposed to another very text-rich data set, and that's the chat logs that the WA police force use to communicate with each other. And so if the data set that was given to us was distributed in this way. So it had mostly images, it had one video, CSV files containing a lot of chats, and PDFs. And our goal, after speaking to the stakeholders, was how do we give them an overview of what happened in each operation, and how do they connect each of the operations to each other, and how do they deep dive into them. So one important data set is image data sets. And we don't see a point in getting AI to describe these images because we can do them ourselves. But when you have a whole folder filled with images, how do you search through them if they don't have captions? And so we've used this technique to search for any kind of image using any kind of description, even though it doesn't have captions. We've then taken the text chats, and we've done a lot with it. We've used Llama 3 and other natural language processing to summarize the text, extract timelines, extract information like locations, geocode those locations, extract relationships, extract entities. And we put it all together into an app where there's the AI engine, there's a database, there's our API, and it connects to a full stack web app. And let's go to the demo. So it's a simple demo where you have all the latest operations. You can click in an operation to get the overview. Seeing more, you can see the timeline, you can see a summary, the key findings, and we've even made the AI give you recommendations on what the next steps are. You can go into it and it immediately gives you all the locations extracted. Next, you can see the images and all the information relevant to it. You can go into the chat logs, and all of this has fuzzy and other smart searching enabled, so you can search for a partial name, a full name, you'll get everything. You can go into the timeline, where there's a detailed timeline of all the events that happened. You can see the relationships within our entity graph, and this extracts structured information from unstructured data. Let's go to the image search. So you can do a text search, but the image search is more impressive. Let's do the man fighting woman or man beating woman. And even though it's not captioned, it will still find it. And there's a lot more things you can try. You can try man standing behind a Gothic structure or anything else. Thank you.
So we'll give you guys a quick rundown of what we've done. So basically, we've generated detailed descriptions of the images that were just shown before using a multimodal LLM. In this case, we've used GPT-4, but in reality, you would use something that's locally hosted. We've extracted text from the attachments, and then what we've done, similarly to the other groups, is we've automatically extracted nodes and relationships between the nodes from the chat history. So the nodes could be things like suspects, locations, vehicles. And then we've created a demo dashboard to visualize some of the data. So for example, here we've got a view of the number of activities associated with each suspect that's been identified within the data set. That way we can identify, high harm offenders and things like that. We've taken account of the number of activities happening at each location so that we can see where there's like, a lot of activity happening geographically. And then I put together this kingpin finder, which is just finding the number of other suspects linked via common activities to a certain suspect. In this case, we've identified Rebecca Lee as being a high priority individual to look into, and I'll leave with you, Akil, to explain the rest.
So apart from the dashboard that we see here, we also have put together a graph database. So that's something that looks like this. So if this is the scene, I want to see any and all relationships with any and all nodes, which in this case can be nodes like activity, location, officer, etc. So I'm just going to run this. And what we see is a very interactive graph database. So now what I'm going to do is I want to find some more details about Rebecca in particular. So I'm going to go to there and type in, okay, Rebecca, who we saw was a highly active suspect in a lot of operations. So I'm going to jump to Rebecca and I can see, wow, she's really involved in a lot of things around the whole data sets, but let's isolate her a little bit more and dismiss everything else. And then let's learn a little bit more about who Rebecca is. Okay, we see that she's involved in Operation Jelly, she's providing financial services, but is also associated with some Facebook Marketplace fraudulent activities. She's got a larger network of fraudsters and is also active on Gumtree. I want to find out who else was involved in Operation Jelly, so I can go onto that and get some more information that Marcus Chen is also part of this and is a very likely accomplice to Rebecca Lee. You can go into more detail as you like with the query section.
Hi everyone, we are DataDucks and this is our solution to Challenge 5. Our solution, Every Second Counts, ensures that all the relevant information is captured during an emergency. It increases the call efficiency by making all information available at a glance. It assists the operator to focus on what's important in a stressful situation, and it stores information in a data lake for further analytics and model improvement. We're now showing you the demo. So we see the operator starts the AI transcription of the call. That's happening in real time. Then the operator adds some notes and comments, which is sent to a large language model in the background. The AI assistant then recommends questions and emergency type, as well as actions to take based on the transcript. There's only less than 10 seconds needed of transcript for those recommendations to happen. Currently, the assistant needs to be triggered, but we want this in future to be automated and real time. Then we can create visualizations with what's happening in the data lake. And we can use those for model improvement, like do sentiment analysis or further cool stuff. This is the tech that we built. We have Google Assistant for the transcript in the backend. That's sending its outcome to the Flask frontend, which sends it to the large language model in the backend, which is hosted on AWS, but can also be hosted locally. That sends the information back, which is then stored in the data lake, which can then be used to visualize on Power BI. What we want to do in the future to improve it is we want to improve the transcription for like background noises, distressed people, screaming, etc. We want to better understand the inputs for the large language model. And we want to integrate a lot more data. And we want to cater to multi-language and translation capabilities and improve the security of where the data is stored and etc.
Well, the expert on all of these things.
Ready to go?
Yeah. Kaya, thank you. Just want to acknowledge the amazing Wanjak Puja we're all meeting today.
Chris Georgia County 911 there. What is the location of the emergency? 4709 48th Avenue. 4709? 4709.
Hello? I see my bosses. I'm sorry? I see my bosses. They are died. I see my bosses. Ma'am, you need the police? Yes, sir, please, sir. Ma'am, I'm not understanding what you're saying.
That's Fuzz AI, and that was just an example of the model that's been built over the weekend, and also to identify how quickly the AI interprets and understands the language, as well as jumping straight to the what's required. So yes, we're solving number 5. We're using voice recognition, converting audio transcript, natural language detection, and we're generating a next best response for the police officers with multiple AI assistants, which is fuzzy. Our model starts with the data coming in directly from the phone call, and multiple different models working in the background and being triggered with, depending on what the input is. I'm just going to explain a little bit more about this. Sorry, I'm going to go back and try and work out why the sound's a bit quiet.
Yeah, I'll step in. So at this point, what we're doing is we built this model. So what you saw before is real data, and we can embed it into the solution. Our solution architecture is based on AI at scale. So we've built this as a foundation model that you can add extra AI layers to it when we come to images and when we come to videos later on. So it's extremely important that we think about what we do next. So we're not building one piece, we're building...
All right, sorry Sarah, I'm cutting you off because we've got 25 seconds. And we can tell more about this afterwards. So we looked also at further advancing into the regional aspects, people that are non-verbal, people that are under trauma and stress and can't respond, and also recognising background noises. We have also got a front end, which is a website. We'll see that later. Thanks, everybody.
Good afternoon. We are Team Vader from UWA. So we're addressing challenge number 5, and our solution is to assist 000 call operators, providing them with real-time transcriptions and also the keywords related to the emergency. And the model will predict the category of the emergency based on the information flow. And we ensure that all the information is being extracted, and the model also makes recommendations about the next questions to ask to the operator. So first we pass the information stream through a noise reduction model, and during the first few seconds we also run an accident detection model that allows us to optionally turn on language translation. We also perform speaker segmentation, which will allow us to differentiate between the caller and the operator, which allows us to improve the accuracy and train the model better. Now this is all happening in real time with minimal delay. We extract the highly detailed text transcript, and we extract the keywords which is used to train the classification model, which also predicts the top categories of categories of emergency, along with the confidence scores, which is dynamic and will change over time as the information comes in. Now the operator has displayed the live transcriptions and also suggestions and recommendations about the next questions to ask. The operator can check off the concerns that have been addressed, and the system will also remind the operator about any unaddressed questions. So this is what the architecture would look like roughly. As you can see, the noise reduction model will also help the operator understand and hear better. And you can see there's a feedback loop, which means that this system is a continuous learning model and it improves over time. This is a rough example of how the UI could look like, and you can see if an accident is detected, the operator will have an option to call in a translator, if depending on how difficult it is to understand, or if the caller is speaking in a different language. So we have a prototype over here. Due to constraints, we're only able to train it on 2 different categories. And you can see it is presenting the keywords that are being extracted. Now this is all happening in real time, and you can see the prediction scores are changing. Now to emulate a real audio stream, we are processing the audio files in chunks.
So the other thing we can do in long term is when we have when they have trained it enough, so we can pass it through an AI index, AI search index in Azure. So that will have the category as the key and then the keywords as the values. So in the long term, it's easy to infer, and the model runs really fast. It will be a deterministic search, hopefully.
Thank you.
Okay. 000.
Hello, this is Amy. He got stabbed just now.
Okay, slow down. Where are you at the moment?
I'm at the front entrance of Spaceship at St. George Terrace.
Okay, so how's the condition of the person who got stabbed?
He's lying on the floor with lots of blood. Someone is doing first aid for him.
Okay, and where's the stabber now?
He went that way.
Where's that way?
Towards the water.
Do you mean towards Elizabeth Quay?
Yes.
Okay, and what's the stabber wearing?
A green a green... I don't know how to describe in English. 綠色格仔 shirt?
Do you mean a green plaid shirt?
Yes, and he's 6 feet tall, around 20 years old, Asian with black hair and a long life.
Being a 000 call operator can be very stressful. The killer could be going around trying to kill other people, and you have to handle such life and death situations within split seconds to save lives. So we are developing an app to try to help them with their work. At the top, it's a real-time transcription and translation feature, and as you can see, Amy struggled to describe the characteristic of the suspect, and it was able to translate from Cantonese to English in real time. And that will help the operator to know what's going on without having to call up another translator. And with that information, all this information will be taken, and our algorithm will start analyzing all this at the back end to try to find out what's the ANSOP code for this one. And in this case, it's 01 homicide, and red color indicates that it's an emergency. There's also yellow and green depending on the urgency. So with this information, it will populate a list of questions that should be asked by the operators to help collect all the relevant information. And all these informations will be populated automatically on the right here, and the operators can make edits to it and check if the information is correct and verify them. By verifying all this information, the data will be fed back into the algorithm and improve the accuracy as more and more data comes in. So for the future improvements, we can also make a two-way translation where the operator can speak in English and the caller will listen as like another language. And also another thing that we can do is that it would be beneficial if the operator can access the camera of the caller to know what's going on. So in summary, we hope to help the operators by making their job easier and reduce the average handling time, which will in turn help to save more lives and make WA a better place to live in. Thank you.
I can go?
You guys ready? We are good.
Okay.
Thank you.
Okay, so that was our problem. And so basically information's missed in two circumstances, where it's inaccurate or not provided. This was shown in the data, and so in this circumstance we've transcribed the audio and it was unintelligible, but we did get some keywords at the end. In the second case it was inaccurate because the retelling wasn't done in a way that one would like it to be done. And then, so basically we've come up with our solution, which is dispatcher assistant, which would be used in the first stages of the emergency response followed by a 000 call. Our solution will assist an operator during the call by identifying keywords in the call based on categories of information to provide recommendations on the incident, emergency response required, incident level, location, and the identity of the caller and those around them. We note that the incident can change as the call progresses in terms of location and incident and the type of incident, and this would be recorded. Ultimately,
ultimately it's up to the operator to make a decision about the incident at the end of the day. So it's more of a recommendation than anything. I'm going to hand it over to Ken.
Yeah. So the solution we came up with, we tried to target a few criteria. One was throughout the call, our machine model will pick up certain keywords from the transcription and also populate this information about the incident, about status, incident type, response levels required, and constantly keeping track of key information in this node panel for the operator to reference. In the case of language barriers, there's a language assistant model that will pop up to assist in cases of language communication issues with pre-trained responses in the language of the choice of known languages. And also, we have also created a post report option that can be curated by a model to curate all this data information into a file, so for any follow-ups or to dispatch to the dispatcher for clarification on the key information is required. Yeah, so that's our solution.
Yeah, good. So hi everyone, we're ex-bug smugglers. Today we're going to be demonstrating Vital Voice. So basically Vital Voice is to assist 00 operators and basically capture key information during a high stress situation. So our approach is one, having real-time transcribing, so a system keeps a conversation log between the caller and the operator, real-time geolocation using that transcript data to ping the Google Maps API to get that data, and 3, the operator assistant. So this is providing questions based on real-time transcripts of what to ask the person. And number 4 is providing incident details capturing. So each person or object creates its own identity, so a car or a person, and all information associated with that will show up as well. And that coincides with number 5 as well. So for the transcription, we use Whisper, which is a real-time transcription service. We just segment that and everything can be replayed to ensure an easy and accurate data recall. For the geolocation, we just use Google Maps and we just ping the Google Maps API based on the data. Real-time suggestions, we fine-tune the LLM model to generate appropriate questions for the operator to ask. The transcript is also processed by the model. And time for a demo.
Emergency services, what is your emergency?
Hi, my friend fell down the stairs.
What is the name and age of your friend?
His name is John Smith, 45 years old.
Where did this occur?
At 220 St. George's Terrace.
How long ago was the incident?
It was an hour ago.
There's a bit of delay, but...
There's a bit of delay, but then eventually the map will zoom out into the location mentioned. There you go.
Sort of.
Should be, yeah.
So the idea is we build sort of an identity profile for each person mentioned in the call, and then we can structure a data object of the whole incident itself, and then that can be referenced in future incidents at similar addresses or any other sort of incidents with those identities as well. Thank you.
And that was us.
Okay, so we're Kwakai, and so we're tackling challenge 5. So our solution, we used Whisper module for the automated transcriptions, and which are then sent to the ChatGPT to generate relevant questions and summaries to support the call operator. So after the call, ChatGPT will generate a memo which contains all necessary information with the 5 Ws about the incident, and then upload it to a group chat So we actually have a chat room, which this enhances the understanding of the situation, increases overall efficiency and accuracy of data input. So the highlight of our design is the chat room. So a link will be sent to the caller's phone to provide access to the chat room. Callers and the assigned officers will be inside the chat room to receive any real-time updates, which creates a two-way communication between the caller and the attending officers. This is a great way to gather the suspect's characteristics and location quickly and accurately. Furthermore, it's really easy to cross the language barrier by just simply implementing a translation inside the chat room. So now, please use your imaginations. Imagine you're inside a you're shopping at a clothing store and an active shooter bursts in. You manage to hide in a closet, leaving a small gap to watch. Hands trembling, you dial 000. But just as the operator answers, the shooter heads your way. You hung up, praying there's 000 don't call back. Okay, for the caller, so by calling 000, a SMS with a link to the chat room will be received. GPS tracking in the link shows the officer your location, and other callers reporting the same incident will be added into this chat room together for further information sharing. And it will be classified by our AI summary system by comparing the location and the descriptions provided by the caller. And the call operator, when the call operator picks up the phone, our system starts the transcription process and summarizing. The operator can use the questions generated by ChatGPT as support to make sure all information is secured and the officers attending are fully informed. The operator shares the summarized info into the group chat with the members, so all the group members are well aware of the situation. And for the dispatch operator, the red alarms on the map shows the caller's location, and there's case ID, incident type, report time will be also displayed. The map helps with visualized dispatch of officers, and officers being dispatched will be pulled into...
Cool. Starting now.
Hello, my name is Abhinav, and along with Wei and Colin, we are addressing challenge number 5 with our application, Siren Script. Here's the presentation, guys.
Come, please.
Okay. Okay, there we go. Go next slide. What's the problem? Responders across WA have to handle multiple complex tasks concurrently. We talked to the stakeholders about this and we derived that it's a very stressful situation. The solution is Siren Script. It provides a full live transcription of the call and extracts key important data that the responders can access in real time and for permanent records. The UI is simple and effective, removing friction for the responder. Our tech stack behind the scenes are simple. We use OpenAI's local whisper model for AI transcription and a Grok API for crucial info summary. For practical police use, we will prefer the local method to maintain data security. Here's our live demo. Our live demo will be between Wei and Colin over there.
Someone just stole my bag. I was walking down James Street and this guy came up behind me and snatched my backpack. Then he ran off towards Robert Street. I'm standing near the James Street bus stop. Yeah, he was a guy wearing a pink polo shirt and black pants, about 6 foot tall, and he had black hair. He had earrings and a tattoo on his right arm, a very muscular arm at that. My wallet, laptop, and a small notebook were inside my backpack. My name is Alex Thompson.
Yeah, that's good. So that's Siren Script, but it's far from finished. We have a lot of extensions to do. One is to do the suggestions, and then use KPIs to track performance across callers to assess whether they are fit for duty or not. Thank you.
We have all heard of Copilot. I'd like to introduce you to CoCop. Now, we know the problem here and what's going on. We identified 2 key areas that we want to cover. Just jump back one. Determine the emergency and ensure all information is collected. Our strategy, choose an LLM open source local model, Llama, fine tune on the audio data and metadata, and identify the key information. What that looked like, we wanted to classify first, and that meant getting the text to speech, speech to text that way, which is happening live right now. And we'll go back. Awesome. So model training, classification, we went through the text, metadata, OpenAI Whisper. That classification then would run through real time. Every 30 seconds that would refresh. So then we have our suspicious activity, our classification, then 30 seconds later, we then get a different classification as well. That's the first one down. Next was to collect all the information available. Cops are armed with guns, we want them to be armed with information as well. That's live text-to-speech, like I said before. Collecting key information, the 5 Ws as has been mentioned before. Same with suggesting the right question. We've gone with looking at what optional questions are available as well. And lastly, I want to highlight we focused mostly on coding, less so on the front end at this stage. The quality of the information was most important, as was highlighted to stakeholders, rather than a solution. David went through and was able to build a model and put it into a chatbot format. This we would pass through the text from the speech. Lastly, wireframe, what this lovely solution would look like when we do deploy it. We'd start with the classification model, so we want exactly what's happening first, then live speech to text, suggested key information, and then looking at suggested question as well. Future state, fine-tuning the classification model. There's a data dictionary with all the questions that we were told about. Speech to text to image was a suggestion we looked at, but didn't have time to explore. And lastly, to train the model on that question dictionary as well. Thank you. That is our CoCop.
Hello everyone. My name is Namish and I'm from Curtin University. And my team members are Clarence Shen from Curtin University as well, and Jaden McQuaid from ECU. And we are presenting on the topic of ensuring the efficient handling of 000 calls, because asking the right questions are really important to understand the problem and get to the solution. So the problem we are focusing on are the incomplete information collection, because that's a big problem, because the person is panicking and maybe the situation is not right. The second problem is the errors in recorded information, because as I said, like the person is panicking and he might be not speaking fluently and not able to speak properly. Third problem is the high stress environment. Fourth is the language barriers, because maybe the person is a Spanish speaker, a Chinese speaker, and he might not able to speak proper English. The fifth problem is the poor audio quality. And the last problem we are focusing on is determination of sufficient information. Okay, I would like to hand over to Yoshan for a resolution. Thank you.
Speaking of the resolution, we identified that we are gonna using some like AI, voice AI to analyze the voice of the calling and to to interpret them into the transcriptions in the text way, and also maybe like a translation of the foreign language into English will be more sufficient for the officer to read on. We would also apply some chatbot assistant in the future. We'll be providing some related dialogues for the certain circumstances to provide a sufficient help for the people in really need. We would have further discuss of the audio enhancement by Jaden. Thank you.
Alrighty. Hello everyone. So we do have a bit of a video around how it's meant to operate. You are going to notice that it automatically picks up the address, and if we just anyway, so you do also notice there is a prompt console which prompts for any questions. This is where any input is inputted by the handler, and then we also have the final portion that's going to be transmitted to the officers attending. Oh. Okay, cool. So we don't have any audio, but thank you.
Okay. All right, on schedule. Well done, team. Thank you for that. That's very appreciated. Big hand round of applause to all of you. All right, the judge is going to retire